Yeah, welcome again. Now we are in the first lecture of example code for model-free control. And in this video, we will show you a QLearning agent that actually solves the FrozenLake environment that we also used to solve in the dynamic programming video example that we used to evaluate using TD Learning in the previous video. And today we're going to talk about QLearning exactly on this environment. As usual, I will stop showing you my face cam, and I will shortly go into the Jupyter notebook. I start my environment, and I will start a Jupyter notebook, which is actually in here. I will open the QLearning environment that you can also download on the web page. And yeah, so that's what you get. Here's our QLearning agent that you can download. If you click on it, you will see familiar elements that we also have used to use in the previous videos. To remind you about, our MDP is a lake actually that's defined by a grid world. And we have a starting state, we have a goal position, we have icy elements, and we have holes that we do not want to fall into. We do not get any reward in the holes, but the episode ends, and in the goal state the episode ends, but we instead get a reward of +1. Yeah, so actually as simple as it is, this is the QUpdate function that you also know from the slides and the lecture videos. Which simply is, so the update you also know from the TD Learning. Yeah, so that is the definition of our QLearning agent. As in the TD Learning example too, we have the imports that we usually need. We import the OpenAI gym environment, for which you got also an in-depth intro in the last video. Then we use NumPy for random number generation and convenience in handling numbers and arrays. And matplotlib to give you some plotting. This is the definition of the QLearning agent. The QLearning agent is defined by the discount factor. We also know this from the TD Learning agent. We have a learning rate, and we have our epsilon for our epsilon greedy exploration. So we just initialize our agent. We initialize the terminal states of the MDP so that we actually know them. And we initialize a QTable. So in this case, the QTable is somewhat more complex than the V function table, because actually the number is also not only defined by the states, we have 16 of them, but also about the actions, and we have 4 of them, so it's 16 by 4. Yeah, so equal as in the previous examples and videos. And what's now different in direct comparison to the TD Learning agent is actually the action selection. So actually the policy we run in the TD Learning, we just evaluated a random policy, or maybe you just played around a little bit with the policy. It was a uniform distribution where we selected with bins our actions, and we uniformly distributed them. And in here now we have a real policy that we actually use. This is just a random number between 0 and 1 that we can actually use to calculate together with our epsilon if we actually perform an action that we actually, so if we actually perform the greedy action. So in this case, our trade-off is larger than the epsilon, which actually means that our action is selected using the argmax of our QTable. So this is just using our QTable at state S and selects the argument that maximizes the second value in here, which is just given by NumPy argmax. So this is why actually NumPy is very convenient. And this returns the action that our agent would take in this state. So what you see now is, in contrast to the TD Learning agent, where we actually we did not make any use of S. In this case, now we really use S in order to draw an action from our QTable that actually maximizes our value, our return. Yeah, or in all the other cases, depending on the epsilon value, we just use a random action that's given by the definition of the action space of the environment. Yeah, we just return this action. and to the guts of to the agent itself in order to just update our Q function. Is basically this function here, the update function that's given by QLearning, actually implemented as a Python code, which basically says that our QTable at SA should be our QTable SA plus our learning rate times our reward, our current reward we get at this time step, plus the discount factor of the upcoming state. But in this case, in contrast to Sarsa, we take the upcoming Q value that actually from the state that actually is the maximum, which gives us here now not the arc max but the max. We actually want to know we want to have as a backup or as a baseline actually the maximum Q value that is achievable from the upcoming state S underscore. This is actually the Q function, the Q learning of policy update minus the current estimation at this point. And this max value is actually this one where we have the difference to Sarsa, where we make this off policy backups of our Q function. Yeah, so this is the QLearning agent. We can just run it, and it's done. It's simple as it is. It's very few actual lines of code that lets us here do the epsilon greedy policy and our Q function update. So this is everything we need. Here's our base loop. What we do here usually is that we initialize our gym environment using OpenAI Gym. So we take FrozenLake v0, which we also used in the previous lessons. Then we implement a schedule for our epsilon greedy policy. This is actually what we also discussed a little bit in the lecture, that you in reinforcement learning, what you usually do is that you will start with a very, very large exploration factor. In this case, you would start with a maximum epsilon of 1, which basically means that you totally explore in the beginning because you really have no idea, and you know that your current estimation of your Q table is random anyway. So what you want to do is you want to maximally explore the environment, and you want to steadily decrease it with this one until you reach some baseline minimal epsilon of 0.1, which is then the minimum exploration probability. And yeah, so you then what we next do is we initialize our agent. We want to run for 50,000 episodes. We keep track of the rewards, and then we iterate over the total episodes we want to run. This is the base loop that you also saw in the TD learning example. You keep track for every episode of the total rewards, and you initialize your FrozenLake MDP and get the initial observation or state. And what you now do is also very similar to the TD learning example. You select an action using your agent's evaluation function, and this one is now really applying an epsilon greedy policy. Yeah? So actually in here you actually select an action using the epsilon greedy policy, and you execute this action actually in the environment. So given the action to your environment, the environment is in the current state S. You get returned as underscore your current reward and the flag if you're done or not. And with this information actually you can perform the QLearning update, which is actually the update of the Q value of the state action value function using your experience sample SR, as the state where you was in, the action, the reward, and the state you're currently in. And this update is actually not done with the actual Q value. You would use your, depending on your policy in here, but using the max operator in here. Yeah, so then you reset the state to the current state. You add it to your total rewards you actually obtained through the episode. And in this case, what you would do is you want to adjust your exploration rate, which basically means that you say, so this is a function that you always find also in reference implementation, that you steadily decrease your value function, your exploration rate until you reach your minimum epsilon. So this term will finally go to 0, and then you will end up with a minimum epsilon. Yeah, so if you run this one, you actually get the initial QTable in here. This is what we print out from here, and now this thing is running for a while until in the final end we get the final QTable. I do not know exactly how long it runs. We will just take our time and maybe wait for a couple of seconds, and I use the time to actually get some water. Yeah, so here we are. This is the final QTable. In this case, not having only 16 values, but 16 times 4 values. For each of the states, we actually get a value of the actions. So feel free to play around with it as in the TD learning example. And what's important now is actually if you have calculated your QTable, you want to actually evaluate your QLearning agent after the training. And what you see here is actually different episodes starting from the start state and behaving using the greedy policy in this case. So what you see here, we select an action, and we have a greedy policy. In this case, we select an action and we do not update the Q function, which basically is nothing else than running our agent in the environment and collecting experience samples. And what you see below here is different episodes where we have a start state and where we always start here. And this is actually saying where we ended the episode. We not always reach the final goal position. This is because we have the stochasticity in the environment. So we get it for some times. So we actually reach this one. But at some points, the stochasticity in the environment really does not apply the down function, but steers us to the right, which basically ends the episode too early. Yeah, so we run this, and you see that nevertheless, after 300 episodes, our mean reward is 0.63. The best one we could actually achieve would have been 1. You see that in many situations we actually obtained a positive reward of 1 as we actually reached the goal state. But as there is ice on the ground, and as this although we actually use the perfect action, we might not end up in the state we are actually hoped to end up in. Which basically means that this is a very good value we can actually reach with this environment, and this is actually the result we want to have. Yeah, so feel free to also play around with this one. You can also play around with the stochasticity in the environment, look into the implementation, and turn around a little bit the probability transitions. You can increase them in order to, you can decrease the stochasticity in order to make everything a little bit more deterministic. So then you will have it a little bit easier to actually evaluate if your QLearning agent is really performing well or not. Play around with the decay of the epsilon parameters for your exploration rate. Play around with discount factor and learning rate in order to get to know how QLearning actually performs and what's all behind it. Yeah, so this is QLearning. This is also the last video that you actually get from Model Free Control. And the summary is still on, so actually you will get a summary video on Model Free Control. But what can I say now is that the motivation for everything that's coming beneath or behind the next lesson actually is that what you currently have seen is that we actually use the table to actually keep track of our value functions, so either the state value functions or the state action value functions. But you could imagine if you increase the state space that you actually will increase quadratically, maybe even depending on how your action and states are actually defined. And you might want to see that, or you might want to expect that this might be too big to actually hold this in memory. And there is solutions to actually get rid of it and discretize things, or taking bins of certain states. But everything like this is just not a real thing, which is the basic motivation for lesson 5, where we actually talk about function approximation techniques. Yeah, so see you in the next video.